Hi guys, we're going to go ahead and get started with our final unit in AP Chemistry, Unit 9, and we are actually going to go through all of these sections. It's kind of split up into two parts. The first part is some thermodynamic stuff, and then the second part of Unit 9 is electrochemistry. And so I'm going to do the videos in two sections, and so this first video is going to go through all of that extra thermodynamic information, which is sections 9.1 all the way through 9.6. So in this first part of Unit 9, a key term for us is going to be this term spontaneous. But when we're dealing with this term on the AP exam, it's also going to be referred to as thermodynamically favorable, which basically just means a reaction that will take place on its own, form products without any outside intervention. The energy that's being absorbed or released and the organization of everything involved is such that the reaction will take place without intervention, whether it is fast or slow. So we'll look at some examples as we get through this unit, but we need to understand some terms before we can understand this whole thermodynamically favorable idea. We need to know what entropy is. So entropy is a term that you have probably heard before. It is a measure of disorder. Normally, they refer to this as like our second law of thermodynamics, and that the entropy of the universe is always increasing. But when we're talking about chemical um, reactions, the entropy has to do with disorder, how many molecules there are they solids, liquids, or gases? Higher entropy values, so we're going to be using the letter S to represent entropy. Higher entropy means more disorder. So molecules that are at high temperatures have greater entropy because we know that higher temperature molecules are moving around faster, and so faster molecule velocity represents more disorder. If you have more moles of something, it's going to have greater entropy. It's going to be considered more disordered. As far as our states of matter go, we've got solids, liquids, and gases. Um, as we go from left to right on this line of states of matter, gases are going to be the substances that have the most entropy because we know our gas molecules are spread out all over the place and they're moving around really fast, where our solid molecules are all organized in a specific pattern. And so that would be considered to have low entropy, gas molecules having high entropy. So we're going to be dealing with positive delta S values and negative delta S values. So positive delta S means an increase in entropy. That means more disorder. And negative delta S values represents a decrease in entropy, which just represents more order. And so there's a lot of different ways that we can go through and do these calculations. We have done a calculation similar to this before with delta H values, that we can calculate delta H if we know the products and the reactants. We can take our delta H values of all of our products, subtract the delta H value of all of our reactants. We can do the same thing with entropy values. And so if we're looking in this example to calculate delta S for the formation of ammonia, I can go ahead and calculate delta S by taking my product entropy values and multiplying it. So my product entropy value of NH3 is 193. I do need to multiply it. Remember when we did this with delta H values, that we multiply it by the coefficient that's in the chemical reaction. So 2 times 193 minus my reactants. My reactants are going to be N2, which is 192. And hydrogen, this is actually a typo, you guys. This should be a 3 in front of H2 to balance that equation properly. So plus 3 times 131, that's going to give us a negative 199. Let's talk about our units for entropy. Joules per mole Kelvin. That negative value for delta S means that we're going to have more order. Now, let's look at if that makes sense based on what the reaction looks like. Over on the left side of my reaction, I have 4 gas molecules I don't really have a lot of room for that, but there are 4 gas molecules over on the left side. There are only 2 gas molecules over on the right side. So as I go from 4 to 2 gas molecules, that is going to be decreasing in entropy. It's going to be more order because I'm going to have less stuff floating around after the reaction takes place. And so that does agree with my negative delta S value for decreasing entropy, which means more order. Another thermodynamic quantity that we need to be familiar with is this delta G. So delta G is called Gibbs free energy, and it's the amount of energy that's available to do work. It's kind of the combination of everything. Once a chemical reaction happens and we combine what's going on with delta H, what's going on with delta S, how are those things combining together to give us this overall picture of the energy that's involved? And so we can calculate that by doing products minus reactants also. But there is also this equation that relates all of those things together in one, where we have delta G as our Gibbs free energy. Oh, that should be a B. Gibbs free energy. We'll talk about units here in just a second. Delta H is our enthalpy values that we talked about back in Unit 6. Delta S is our entropy. And then T represents our temperature. This is always going to be plugged in as Kelvin. If we have delta H, delta S, and we know the temperature, we can plug it in and calculate delta G. Now, the reason why delta G is so important is because we want to figure out, always our goal is to figure out if delta G is going to be positive or negative. The big idea for this section is we're going to be talking about if reactions are thermodynamically favorable or not. And so if we have a negative delta G value, then it would be considered a thermodynamically favorable reaction, and one that will happen on its own without any outside intervention. Let's review some of these thermodynamic quantities real quick, delta H, delta S, delta G, just remembering what positive and negative values for these represent. So delta H is from Unit 6. Positive delta H represents a reaction that is endothermic, and negative delta H represents a reaction that is exothermic or losing energy. So really important just to know what those values represent. Positive delta S represents increasing entropy, which means more disorder. Negative delta S represents decreasing entropy, which means more order. And for delta G, this is all going to be about thermodynamically favorable or not thermodynamically favorable. So I'm going to abbreviate this. Negative delta G is thermodynamically favorable, but this, you guys, is a really important term that you use this term on the AP exam, not the term spontaneous, because it is a big picture of what's going on with all the thermodynamic quantities. So if you get negative delta G, it means it is a thermodynamically favorable reaction that will take place on its own. If it is a positive delta G, then it is not thermodynamically favorable. Let's take a look at an example here where we have delta H is 23.5 kilojoules per mole. Delta S is 34 joules per mole Kelvin. Now, something that is important for you guys to notice about units. Always pay attention to units. Delta H in this problem is given to us in kilojoules per mole, and delta S is given to us in joules per mole Kelvin. Now we end up multiplying delta S in our equation. Delta G equals delta H minus T delta S. We multiply our delta S by temperature, so that Kelvin goes away as far as the units go. But we've got 1 in kilojoules, 1 in joules, and that's usually the case. They usually give you delta S in joules. So I'm going to go ahead and convert that, divide it by 1,000, and to convert it into kilojoules per mole Kelvin. So that's going to give me 0.0345 kilojoules per mole. Now, if I'm looking for the boiling point temperature, that means I am looking for T in this equation. I have delta H, I have delta S. Something to know, boiling point temperature. At the boiling point, that is considered to be a situation of equilibrium with our phases and everything that's going on there. And so at equilibrium or at any kind of boiling point or melting point, delta G is going to equal 0. And so 0 is going to be equal to delta H minus T delta S. I'm trying to solve for temperature. So I'm going to bring this over to the other side, get T delta S equals delta H, and my temperature is going to equal delta H over delta S. And I can just go ahead and plug in my values, 23.5 kilojoules per mole for delta H. And I've got 0.0345 kilojoules per mole Kelvin for delta S. That is going to give me my temperature, 681 Kelvin. This next chart is just really important for you guys to understand and conceptually be able to figure out this chart on your own. I don't want you guys to try and memorize this equation, so I am going to go through the process of, what it takes to fill in this chart. Basically, what we're looking at are different combinations of delta H, delta S, and figuring out if these different combinations are going to give us a thermodynamically favorable reaction based on what my answer for delta G is going to be. And so even if we don't know numbers, if we try and just figure out conceptually by plugging in positives and negatives, we can figure out if the delta G is going to be a negative or positive number. We can go ahead and look at this equation that we've been talking about. So delta G equals delta H minus T delta S. So let's look at this first situation here. If I have a positive delta H and a positive delta S value, and I plug it in here, I'm going to be taking a positive number and I'm going to be taking a positive number, and I am going to subtract a positive number. What that's going to give me, I'm looking for, is that going to give me a negative answer? Well, it kind of depends on how big this positive number is. If this number is big enough and I subtract it from a number that's smaller than it, then it will give me a negative. If it's not very big, then I'm going to end up with a positive answer. So I can have a positive or negative answer here. And so trying to figure out if my reaction is going to be favorable has to do with this number. And so it's going to depend on the temperature. If I get that number big enough, then it will make my delta G negative. So we're going to say that this is favorable at high temperatures. Because if I have a big temperature number, that's going to make this large enough to give me a negative delta G. So let's do it for the next one. So negative delta H minus a negative number for delta S. Now I could get, depending on, again, how big this number is, I could get a negative delta G or I could get a positive delta G. So I could get positive or negative. It will be negative, delta G will be negative at low temperatures. Okay, let's take a look at if I have a positive number minus a negative number. That is going to give me a positive answer always. And so if I always get a positive answer there, delta G is positive, that means that it is never going to be a thermodynamically favorable reaction. If we think about what that means, in order for something to absorb energy and also become more ordered, that's not something that's going to happen on its own without any outside intervention. So it's never going to be considered spontaneous or thermodynamically favorable. If I have my next one right here, a negative delta H value, and I subtract a positive number, that is always going to give me a negative answer for delta G, and it will always be considered a spontaneous reaction. Another common question is to be asked what temperature a spontaneous reaction will take place, or when will a reaction become thermodynamically favorable? So we're going to use this same equation, delta G equals delta H minus T delta S. Now, if I can figure out where delta G is 0, then at what temperature is delta G 0? Then I can figure out at what temperature that reaction becomes spontaneous. So I'm going to go ahead and rearrange this equation first, just like I did last time. So T delta S equals delta H, and temperature will equal delta H over delta S. So delta H will be 31 kilojoules per mole. Let's remember that my delta S value is given to me in joules. So I need to divide that number by 1,000 and get 0.093 joules per mole Kelvin. That's going to give me a temperature of 333 Kelvin. So if I plug in 333 Kelvin right there for my temperature, it's going to give me 0 for delta G. So when does it become spontaneous? It's going to become spontaneous at temperatures greater than 333 Kelvin. If I plug in 334 right here, then that's when my delta G becomes a negative number and when it becomes thermodynamically favorable. And for this next section, 9.4, it's just a conceptual thing for you guys to understand what this term kinetic control means. Basically, if we have reactions that are considered thermodynamically favorable, which means they have a negative delta G value, but they don't make products at a measurable rate. And so the idea is, what's going on there? So if that's the case, if it has a negative delta G, but you're also not producing products at a measurable rate, we would say that those reactions are under kinetic control. And what that means is what I have highlighted here. That means that those reactions have really large activation energies. And so it does take a lot of energy. Delta G is negative, but it does have to absorb a lot of energy in order for that reaction to begin. And so that's just a conceptual thing. If it's not producing reactants or products at a measurable rate, it's because there's a large activation energy. Yes, we can add a catalyst and it'll lower the activation energy there, but a catalyst doesn't change anything else. Delta G, delta H, delta S all remain the same, but it just speeds up that reaction because it lowers the activation energy. Some other really important conceptual things you guys have to understand. What I have highlighted here, these relationships between delta G and K, our K value, our equilibrium constants. If we have a negative delta G value, which means delta G is less than 0, means it's negative. That means it's thermodynamically favorable. If it's thermodynamically favorable, that means it's going to make products on its own without any outside intervention. And since our K is equal to products over reactants, oops, then our K value is going to be greater than 1. So this right here, really important. And I think I put it down here as well. If G is less than 1, if G is negative, then K is going to be greater than 1 because you're going to have more products being formed. If G is greater than 0, it means that delta G is positive, which means it's not thermodynamically favored, which means you're going to have more reactants at equilibrium. So our K value is going to be less than 1. Really, really, really understand that relationship right there. If G is close to 0, then that means we're at equilibrium and K will equal 1. Okay, so let's take a look at this equation right here. This equation gives us the relationship between delta G and K, and if we know one of them, we can calculate the other one. Temperature is always going to be in Kelvin. This R, we've seen R before and the ideal gas law, and it was 0.08206. The R here is going to be 8.314, and it's given to you on your equation sheet. So just know when to use it. I think this is the only time, the 8.314, that you guys need to use that R value. If we are going to calculate the K value and we know delta G is negative 33.3, the one thing that is important here is to recognize that that I need to actually, when I'm using this equation, it needs to be in joules per mole Kelvin. So what I need to do is I need to convert kilojoules per mole, or actually kilojoules per mole, to joules per mole before I can plug it in here, because the units for R include joules and Kelvin as well. And so we need to go ahead and make that conversion. So we need to multiply by 1,000. So that's going to give me negative 33,300. That's going to be in joules per mole for delta G. I'm going to go ahead and go up here. So now I'm going to have negative 33,300. That's going to equal negative 8.314 times the temperature, which is 298. Times the natural log of K. So now I want to get natural log of K over by itself. So I am going to divide by negative 8.314, and then I'm going to divide by 298, and that is going to give me 13.44. Now remember that when we get rid of the natural log, we're going to use E. So K is going to equal E to the 13.44 power. And that is going to give me a really big number. So K is going to 10 to the 1, 2, 3, 4, 1, 2, 4, 5. And so that's a big K value, which makes sense. If I have negative delta G, that's a thermodynamically favorable number. Negative delta G means I'm going to have a K value that's greater than 1, which I do, 6.87 times 10 to the 5th. And the last section that we have for 9.6 is coupled reactions. Now, the good news is we kind of actually already know how to do this. We just didn't call it coupled reactions and we didn't use it for delta G, but it's basically Hess's law. We're going to take unfavorable reactions, and if we pair them with another reaction, we can make them thermodynamically favorable. And we can pair them with a reaction that shares a common intermediate, and we can use Hess's law to calculate delta G. So what we're going to do right here is take a look at our reaction and figure out what we need to do in order to get my overall reaction. And I'm realizing right now that I didn't put the overall reaction. So let's go ahead and put that down here. So the overall reaction we're looking for to find delta G for is going to be iron 3 oxide plus 3 carbon monoxide. And that's going to produce 2 irons and then 3 carbon dioxides. So looking at what I need to have happen here, my first reaction, I can leave it as is because everything, I have 1 iron 3 oxide. But in my overall reaction, I've got 3 carbon monoxides, 3 carbon dioxides. So I do need to multiply this reaction by 3, which I'm going to go ahead and also multiply my delta G by that number so that it can give me the overall reaction. My intermediate is going to be O2. So this is a good review of some of the things that we did in Unit 5. Intermediates, they are products of our first reaction and reactants in the following reaction. They get used up, they get crossed out. So oxygen is the intermediate there. Now I can go ahead and add these numbers together. So 742.2, add 3 times negative 283.5 is going to give me a delta G value of negative 108.3. That's in kilojoules per mole. So I have a negative delta G value, which makes it thermodynamically favorable. Okay, that is everything thermodynamics you need to know, you guys. Delta G, delta S, relating that to our equilibrium constant. When we come back to class on Monday, we are going to be doing a lot of thermodynamic equations and practice with all of these sections, and then we will move on to the last section of all of our curriculum with electrochemistry in the next video. So I will see you guys in class. Bye.